I had a funny moment this morning. I was standing in line for coffee, leaning against the brick wall of the cafe, just, staring at my phone.
Right.
And it just hit me. I was leaning against a piece of technology, a really, really old piece of technology.
That is the common perception, isn't it? That
Okay.
it's just there.
Yeah.
But if you actually stop and look, and I mean really investigate, a masonry wall is a machine.
A machine. How
It's
so?
an active system. I mean, it's managing water,
Mm.
it's handling gravity, it's dealing with thermal energy. It is doing a lot of work while you're just standing there drinking your latte.
And that is exactly why I wanted to do this deep dive today. We're looking at a stack of research that, honestly, it completely changed how I look at the city.
Uh-huh.
We're talking about the history of masonry, but maybe more specifically, the glue that holds civilization
That's a
together.
mortar.
The mortar. And I'll be honest, if you had told me yesterday that I'd be fascinated by, like, gray paste, I would have laughed.
It doesn't sound very exciting on the surface.
But this story is wild. We're going to go on a journey that starts with, believe it or not, the Tower of Babel. It goes through a massive fire that burned down London and literally changed the law. And it ends with a marketing scam in the 1800s that gave us the most common building material on Earth.
And we absolutely cannot forget the twist ending.
Mhm.
This story has a very specific and somewhat tragic twist ending.
The twist is the best part. It's the part where we realize that our modern upgrade to that glue, the stuff we thought was stronger, faster, better,
Was actually destroying the very history we were trying to save.
exactly, it's destroying it.
It is a classic case of engineering hubris, really. We learned the hard way that stronger doesn't always mean better. Sometimes stronger is actually fatal.
So that's our mission today. We are going to trace the arc of masonry to understand how we went from, baking bricks in the desert to a chemical revolution that changed the planet.
Yeah.
And along the way, we are going to figure out why my house is still standing and why some historic buildings are literally exploding in slow motion.
I think we can manage that. And to do it right, we have to go way, way back. We aren't starting in the Victorian era.
No.
We were going back to the biblical beginning.
Right. The first major data point in our source material is Genesis 11, the Tower of Babel.
Right.
Now, usually when people talk about Babel, they talk about languages or hubris or, theology.
Of course.
But you look at it and you see a manufacturing report.
I can't help it. I'm an engineer at heart. When you read the text in Genesis 11, verse 3, it's surprisingly specific about the technology.
Okay.
It says, "Come, let us make bricks and burn them thoroughly." And then it adds, "And they had brick for stone and bitumen for mortar."
Okay, let's unpack burn them thoroughly. That phrase really jumps out at me. It implies there's another way to make bricks that isn't burning them thoroughly.
Exactly. You've hit on the key point. The standard way to make a brick in the ancient Near East was to take mud, shape it, and just let it dry in the sun.
Simple enough.
It's cheap, it's easy, but it's weak. If a sun-dried brick gets wet in a flood, what happens?
It just turns back into mud. It dissolves.
It dissolves, right?
Yeah.
But burning thoroughly means they were using kilns. They were firing these clay units at temperatures probably exceeding, 1,000 degrees Celsius?
Wow.
That creates a ceramic bond. It essentially turns the clay into artificial stone. It becomes waterproof and incredibly durable.
So it's a completely different material at that
A
point.
totally different chemical state.
Yeah.
And then there's the mortar, bitumen. I looked this up. It's basically asphalt, isn't it?
Yeah.
It is. It's naturally occurring tar or pitch. Now, think about the context of the Babel story. This is taking place on the plain of Shinar, and the narrative places it shortly after the Great Flood.
So you have a civilization with a very fresh, very traumatic cultural memory of being completely wiped out by water.
Exactly. And they're building in a river valley. So what do? They don't just stack rocks. They engineer a system.
Okay.
They use high-fired waterproof bricks, and they use asphalt mortar, which is a waterproof sealant.
They were building a structure designed to survive another flood.
That is the engineering argument, yes. They were building a flood-proof tower.
That puts a whole new spin on it. This wasn't just, let's build a tall tower. It was, let's build a bunker.
It was advanced material science in the 3rd millennium BC. And the key takeaway here is that masonry wasn't this slow, accidental discovery where, cavemen were piling up pebbles.
Right.
The biblical record shows it as an intentional industrial technology from the very start. They were manufacturing their own geology.
They were making their own rocks because they didn't want to rely on what nature gave them.
Precisely. And that theme of manufacturing sort of shifts when we look at the next big data point in the text, the Exodus.
The Israelites in Egypt. This is Exodus 1 and 5. The vibe here is totally different. We aren't talking about high-tech waterproofing anymore.
No. not at all.
Okay.
Here we are seeing the other side of masonry, mass production. Exodus 1.14 speaks of hard service in mortar and brick. And then in chapter 5, we get that famous conflict about the straw.
Right. Pharaoh says, "You shall no longer give the people straw to make bricks. Let them go and gather straw for themselves."
Yeah.
I have always wondered about the straw. I mean, was it fuel for the kilns like we just talked about?
In this context, almost certainly not. We're likely looking at sun-dried mud bricks here, the cheaper, mass-produced alternative to the Babel bricks.
Okay.
Now, mud is great, but clay has a problem. As it dries, it shrinks. And when it shrinks, it does what?
It cracks.
It cracks a lot. So the brick falls apart before you can even use it.
Right.
Unless you add reinforcement. The straw acts as tensile reinforcement.
It holds it all together.
Yes, it's the ancient equivalent of rebar in concrete or fiberglass in plastic. It holds the clay matrix together while it dries, preventing those catastrophic cracks.
So we have two really distinct technologies here in the ancient world. The high-heat ceramic waterproof system of Babel, and then this composite, fiber-reinforced mass production system of Egypt.
And look at the scale in Exodus. This isn't a small-time operation. It depicts a massive industrial complex.
Yeah.
We are talking about quotas, supply chains for stubble and straw, overseers, a labor force of thousands. Masonry here isn't a craft. It's the engine of the state. It defines the economy.
It really grounds these stories in a kind of physical reality. But let's fast forward a bit. We get through the desert. We get to the monarchy period. Solomon's temple in 1 Kings 6. The sources all highlight this as a huge transition point. We aren't playing with mud anymore.
No. This is the era of hewn stone. And there is this beautiful, slightly eerie detail in 1 Kings 6.7.
Oh, this is the part I love.
It says the temple was built with stone prepared at the quarry, so that neither hammer nor axe nor any tool of iron was heard in the house while it was being built.
Silent construction. That sounds almost impossible. I mean, I've had contractors fix my bathroom and I could hear them from down the street. How do you build a massive stone temple in silence?
It implies a level of logistics and prefabrication that really rivals anything we do today.
Yeah.
Think about it. You're cutting these massive limestone blocks miles away at the quarry. You have to be so confident in your measurements, your tolerances, that you know for a fact that when that stone arrives on site, it will fit perfectly next to its neighbor.
Without a single chip or adjustment.
Without a single tap of a hammer.
That is high-stakes Lego.
It is extreme precision. Now, the text doesn't explicitly discuss the mortar recipe here, but physically, for a structure of that scale, you cannot just stack rough stone. Even with polished stone, you need a bedding layer.
A cushion, is that the idea?
Exactly, a cushion, a very fine lime mortar or maybe a clay slip. Its job isn't necessarily to glue the stones together like superglue. Gravity does most of that work.
Right.
The mortar's job is to distribute the load. If you have a microscopic high spot on one stone and you stack 10 tons on top of it, all that weight concentrates on that one tiny point.
And the stone cracks.
It shatters. It just explodes.
Yeah.
So you need that bedding layer to ensure the weight is spread evenly across the entire surface.
So even in this stone temple, the mortar is still the unsung hero. It's allowing the whole thing to work.
It's the critical interface material. By the time we get to the New Testament, around 0 AD, it seems like this knowledge foundation, stone, mortar, it's just common cultural knowledge.
Right. It's not some secret art.
No, it's the background radiation of the culture. When Jesus tells the parable in Matthew 7 about the wise man building on rock and the foolish man on sand,
he doesn't have to stop and explain the soil mechanics.
he doesn't have to say, now, sand has a low bearing capacity and is subject to liquefaction. The audience just gets it.
Yeah.
They lived in that world. They understood that a building is only as good as its connection to the earth. Masonry was the dominant technology of their world.
So we have this biblical foundation. We have fired bricks, sun-dried bricks, precision stone. But then the Romans enter the chat.
Ah, the Romans.
And if we're talking about masonry, I mean, you have to talk about the Romans.
The Romans are the giants. We are still living in their shadow in so many ways. And the reason they were such incredible builders wasn't just their organization, which was legendary.
Yeah.
They unlocked a secret weapon, a chemical secret.
The secret sauce.
You could call it that. It was volcanic ash.
Volcanic ash.
Specifically, ash from the region of Pozzuoli, near Mount Vesuvius. We call it Pozzolana.
Okay, let's get technical for a second.
Yeah.
Up until this point, most mortar was just limestone mixed with water and sand. That's the basic recipe. What happens when you sprinkle in this volcanic ash?
This is the game changer. Normal lime mortar relies on the air to set.
Okay.
It has to react with carbon dioxide in the atmosphere to turn back into hard limestone. We call that carbonation. But that process requires air.
Which is a huge problem if you're, say, building a bridge pier in the middle of a river.
Exactly. It's the fatal flaw.
Yeah.
If you put normal lime mortar underwater, it just turns to mush. It washes away. It never sets.
Right.
The Romans discovered that if you mix this specific red volcanic ash with the lime, it becomes hydraulic,
Hydraulic.
meaning it reacts with water. The water itself triggers a chemical reaction that makes it set hard rock hard, even while completely submerged.
So they invented waterproof concrete 2,000 years ago.
They did. And that is why the Pantheon is still standing. That is why Roman aqueducts and harbors are still there. They created a material that actually got harder and stronger over time, even in damp conditions.
Which is incredible. But then the empire falls. We hit the Dark Ages. Did we just lose the recipe?
Well, we lost the supply chain. You couldn't easily get high-quality pozzolana from Italy to a building site in northern England anymore. The trade networks collapsed, so the technology regressed.
So what did builders do? I mean, if your glue is weak, how do you keep the castle standing?
You change the design. You compensate. From about 500 to 1000 AD, walls got incredibly thick. They just relied on sheer mass and gravity because they couldn't trust the tensile strength of the mortar anymore. But then as we move into the High Middle Ages, the era of the great cathedrals craftsmanship comes roaring back.
And this leads to something that, sounds kind of boring, but actually changed how regular people lived. The chimney.
It sounds so mundane, but the chimney is a massive technological leap. Before the 12th or 13th century, most houses just had a fire pit in the middle of the room.
And a hole in the roof.
And a hole in the roof for the smoke to hopefully find its way out.
Which sounds miserable. Just smoky, cold, drafty.
Terrible air quality. Just awful.
Yeah.
But as masonry skills improved, builders learned to construct complex, fire-resistant flues that could draw smoke up and out safely.
Which means?
It allows for multi-story buildings, properly heated rooms, a complete change in domestic architecture. It changes society.
But here's a key point from the research, and I want to make sure we hit this. These medieval buildings, cottages, cathedrals, manor houses, they were built with a very specific philosophy regarding water. They weren't waterproof, were they?
No, and this is absolutely crucial for understanding the modern crisis we're going to talk about later. These buildings were designed to breathe.
Okay, let's define that. We aren't talking about air conditioning here.
No. We are talking about vapor permeability. The lime mortars used in the Middle Ages and the Renaissance were soft and porous. Think of them like a hard sponge or a wick.
Okay, a wick. I like that.
If rain hit the brick wall, the water would soak in. That's fine. But because the mortar was porous, air could get in, pick up that moisture, and evaporate it back out. The wall managed its own moisture levels naturally.
It was a dynamic system?
It was a flexible dynamic system. It worked with nature, not against it.
It's designed to get wet and then dry out.
Exactly. And that system worked beautifully for centuries until we hit 1666.
The Great Fire of London.
The turning point.
I mean, it is hard to overstate how big a deal this was. London was basically a timber city. It was a forest just waiting to burn.
And burn it did. It wiped out the medieval city. Something like 13,000 houses destroyed. The shock was profound. And the government's reaction was swift and drastic.
Right.
They passed the Rebuilding Act of 1667.
Which basically said, no more wood.
Effectively, yes. It banned timber framing for exterior walls in the city. You had to build with brick or stone. End of story.
So overnight, masonry stops being just a structural choice or, a style choice. It becomes a safety mandate.
It becomes a fire safety system. The new laws were incredibly specific. They mandated the thickness of walls based on the height of the building. They mandated party walls, these thick masonry barriers between row houses that had to extend above the roofline.
So if your neighbor's house catches fire, it hits that wall and stops. Yours is protected.
Exactly, a firewall. And this is why London looks the way it does today, with all those brick terraces. But more importantly for us, this legislation jumped the ocean.
Right, because early America was so wood-centric. I mean, we had endless forests. Why would you buy bricks when you have trees in the backyard?
Exactly. But as cities like Boston and Philadelphia grew and inevitably burned down, they looked to London for the solution. They adopted those same masonry codes. The beautiful brick row houses of Beacon Hill in Boston or Old City, Philadelphia exist because of those fire codes.
Okay, we're going to hit pause on your training session for just a minute. I know you're probably deep in the weeds of, a flue liner tutorial or something. But we really need to talk about who is actually producing all of this content.
Right. If you're here watching these videos, you're already getting the benefit of the training. But there's a much bigger ecosystem behind this YouTube channel. We're looking at chimneysweeps.com, and it's pretty clear this isn't just a media company. It's more like a funnel, a vetting engine for the industry.
That's a really important distinction, because usually with these online directories, you just pay a fee, you get your pin on a map. Is that what's happening here? Is this just another pay-to-play model?
No. The documentation we have suggests it's the opposite. It seems like they're trying to solve that classic low-bidder problem that plagues the trades. They're not looking for advertisers. They're building a vetted network. And that standard, it seems to come directly from the founder, Ray Gessner.
I was looking at his bio. You don't often see this kind of background. It's this mix of high-level academic engineering and, actual trade mastery. You usually get the guy in the office or the guy in the truck.
Exactly. And that combination is really the key here. Ray isn't just some tech guy. He has a master's degree in civil engineering. He's a licensed professional engineer, a PE in multiple states.
But he also holds master licenses, HVAC, gas fitter, plumber.
And he's a certified home inspector through NACI.
So he's looking at a chimney as both a structural engineer and as a hands-on inspector. But how does that actually translate to the platform? Is it just good branding?
It seems to be baked right into the gatekeeping. Because he understands the physics, the code, the actual science behind it, the platform can enforce a technical standard that, a simple lead gen site just couldn't. Which brings us to their whole gold standard vetting process.
Okay, right. So for the professionals listening right now, the ones who are already doing great work, how does the platform actually verify that? How do they filter out the noise?
Well, it starts with the basics, the non-negotiables. You have to have the proper licensing, general liability insurance, workers' comp, all of that.
The table stakes.
Exactly.
Yeah.
But the real barrier to entry is the CCI exam, the Certified Chimney Inspector Test.
And this isn't just one of those watch a video and click a button certifications.
Oh, far from it. Ray Gessner developed this exam himself to test for technical accuracy, safety knowledge. It's designed to be difficult. It's a filter, plain and simple. It ensures that if a homeowner finds you through them, they're not just getting a name from a list. They're getting someone who passed a really tough technical evaluation.
Okay, so let's say a listener runs that gauntlet. They've got the insurance, they study, they pass the CCI exam, they're in. What's the actual utility for them? Why jump through all those hoops instead of, say, just buying more Google ads?
Because it shifts you from just being listed somewhere to being part of an operational support system. The sources show a few key benefits. First, there's the proprietary inspection report software.
Which I'm guessing is based on those same engineering standards we were just talking about.
Precisely. It automates the reporting, so your paperwork has the same rigor as the inspection itself. Then there's the community. You get access to these monthly online forums, mentorship, networking. It's like a mastermind group for ethical operators.
And that brings us to getting the actual clients. Let's talk about the number 833-CHIMNEY.
That's the engine. The website, that phone number, they drive homeowners who are specifically looking for qualified professionals. These are not people just shopping for the cheapest price. They're looking for vetted expertise for big jobs, relining, structural engineering inspections.
So it creates this kind of feedback loop. You watch the free training, like the video you're probably watching right now, to get better at your job. Then you pass the exam to prove you're good. And then the platform sends you customers who actually value and are willing to pay for that expertise.
It helps the good guys build stronger businesses because they finally stop competing with the companies that are just cutting corners. It really elevates the trade.
So I guess here's the challenge for everyone listening. You are sitting here right now. You're learning for free from one of the best sources in the world. But the real question is, are you ready to capitalize on it? Are you good enough to pass that CCI exam, to join the network, and be recognized as one of the best?
If you think you're operating at that level, head over to the site. Click Join Us.
All right, we'll let you get back to your training now. Thanks for listening. So by 1800, Masonry is the standard. It's safe, it's durable, it breathes, the system works. But the world is speeding up. The Industrial Revolution is here.
Right.
And slow and steady isn't cutting it anymore.
The quest for strength and speed. This is where the chemistry really starts to change. And it begins with a man named John Smeaton in the 1750s.
The lighthouse guy, I've heard of him.
The lighthouse guy. He was tasked with rebuilding the Eddystone Lighthouse on this tiny exposed rock in the English Channel. An absolute nightmare of location.
I can't even imagine. Every time the tide comes in, your work just gets washed away.
He couldn't use standard lime mortar. It sets too slowly. It would just be gone. He needed something that would set now.
So what did he do?
He essentially rediscovered the Roman secret of hydraulic lime. He analyzed different types of limestone and figured out that stone with clay impurities burned into a lime that would set with water.
He reverse engineered it.
Pretty much. And this kicked off a race among inventors to create an artificial stone that could set fast and hard.
And this brings us to the most famous name in construction history, or at least the most famous product name, Portland cement.
The gray powder that built the modern world.
But here's the thing that blew my mind when I was reading up on this. It has nothing to do with Portland, Oregon. It has nothing to do with Portland, Maine.
No, not at all. It is a pure marketing gimmick.
Okay, introduce us to the man, Joseph Aspdin.
So it's 1824. Joseph Aspdin is a bricklayer in Leeds, England. He's been experimenting in his kitchen, and he invents a process of burning limestone and clay and grinding it into a powder. He patents it, and he needs a name.
A good name, a premium name.
A premium name, because he's selling a gray powder. And at the time, the most expensive, high-quality building stone in England was Portland stone, a beautiful white limestone from the Isle of Portland on the coast.
The fancy stuff.
The fancy stuff. Aspdin claimed that his cement, when mixed with sand and water, dried to a color that looked like that fancy stone.
It was a knockoff. It's like selling Rolex-ish watches.
It was absolutely a branding exercise. He called it Portland cement, to associate it with quality and prestige. But here's the funny part. Aspdin's original product wasn't actually what we call Portland cement today.
It wasn't. What was it?
No. He wasn't cooking it hot enough. His process. It was barely better than the hydraulic lime Smeaton used. It was a good product, but it wasn't the revelation.
Okay.
The real chemical breakthrough happened with his son, William Aspdin.
The black sheep of the family, from what I've read.
A bit of a scoundrel, by all accounts.
Yeah.
He fell out with his father, set up his own factory, and started experimenting, trying to one-up the old man.
Right.
And in the 1840s, William figured out that if you cranked the kiln temperature way, way up past 1,300 or 1,400 degrees Celsius, something dramatic happened in the kiln.
What happens to rock at that temperature?
It begins to melt. It fuses together into these hard, dark, glass-like nodules. The workers called them clinker.
Clinker. It sounds like something you'd throw away.
And previously they did. They thought it was overcooked waste, that the batch was ruined. William realized that if you took that ruined clinker and ground it into a fine powder, you got magic.
He found the super glue.
He created calcium silicates. This is the moment masonry changes from a slow drying out process to a rapid chemical hydration reaction.
Okay, we absolutely need to pause here and really explain the difference between the old way, the lime mortar, and this new way, Portland cement.
Yes.
Because this chemical difference is the root of the whole problem we're going to discuss later on.
This is the great divergence. This is the fork in the road. Let's look at the old way first, the lime cycle.
Okay.
You take limestone, which is calcium carbonate. You burn it in a kiln at a moderate heat, around 900 degrees Celsius, to drive off the carbon dioxide. It becomes quicklime.
Which is pretty dangerous stuff, right?
Very reactive, very caustic. You then add water to slake it in a controlled reaction, which turns it into this creamy lime putty. You mix that with sand to make your mortar.
Okay, so now it's on the wall. How does it get hard?
Here's the key. For it to turn back into stone, it has to reabsorb the carbon dioxide from the air that was driven off in the kiln.
It has to drink the atmosphere.
Essentially, yes. It's called carbonation. It happens from the outside in, very slowly. It is a slow, gentle process. It can take weeks, months, or even years to fully cure deep inside a thick wall.
Weeks? I can see why builders might get impatient with that.
It's incredibly slow. But the result is a mortar that is relatively soft, flexible, and, as we said, vapor-permeable. It breathes.
Okay, now compare that to William Aspdin's Portland cement, the new stuff.
Totally different world. Portland cement starts with that superheated clinker. When you add water to Portland cement, you aren't waiting for air. You trigger an immediate chemical reaction called hydration.
It reacts with the water itself.
Yes. Microscopic needle-like crystals start growing and interlocking, like millions of tiny fingers gripping each other, and they do it fast.
How fast?
They'll get an initial set in hours, and it gets hard. Really hard, rock hard.
And it's waterproof.
It is dense and impervious to water. It doesn't breathe.
I can see why the industry just went wild for this. It solves every problem. It's fast, it's strong, it's predictable.
It was a revolution, especially once they figured out how to mass produce it.
Yeah.
In the 1880s, the rotary kiln was invented. This giant, spinning, slightly inclined tube that could cook this clinker continuously. 247.
And in the U.S., we jumped on that bandwagon pretty quick.
We did. For a while, we imported it in barrels, which was expensive. Then around 1875, commercial production started in Pennsylvania, in the Lehigh Valley, the Copley Cement Company.
And that was it.
Once we could make it cheap domestically, the game was over for lime.
It was all about speed and money.
Speed and labor. Think about it. To use lime mortar effectively, you need a skilled mason who understands the material, who knows how to mix it, how to protect it from drying out too fast, how to keep it damp while it cures for weeks. It's an art.
Right.
With Portland cement, any laborer can mix it in a bucket, slap it on the wall, and tomorrow you can build the next floor.
It de-skilled the workforce.
It absolutely did. It allowed for much faster construction with less skilled labor. By the 1930s, pure lime mortar was practically extinct in new construction.
It became a lost art.
Completely.
Yeah.
If you went to a builder's supply house in 1950 and asked for mortar, they handed you a bag of Portland cement. That was just what mortar was.
And for a while, that seemed fine. Everyone was happy. We were building skyscrapers, highways, dams. Portland cement is amazing stuff.
Is a miracle material for modern structures. Concrete, steel, modern hard bricks. They're all designed to be part of a rigid, strong system. The problem started when we looked back at our old buildings, the ones built before 1930, and decided to fix them with our new miracle glue.
This is segment 5, the oops moment, the restoration crisis.
This is the tragic part of the story. You know, Smeaton and Aspen, they were trying to solve a problem setting underwater or setting fast. They never, ever anticipated what would happen when you mixed their new chemistry with the old physics of traditional buildings.
So, paint the picture for us. It's 1970. You own a beautiful 200-year-old brick row house in Philadelphia. The mortar is getting a little sandy, maybe a little crumbly.
Right, it's showing its age.
So you do the responsible thing. You hire a contractor to repoint it.
Repointing is just the process of scraping out the old, failing mortar from the joints and putting in new mortar.
Correct.
The contractor arrives. He's got a bag of Portland cement on his truck, because that's what everyone uses. It's all he knows.
Of course.
He thinks, I'm going to do a great job. I'm going to use this super strong, modern cement. It will last forever.
Stronger is better. That's the logic. It seems so intuitive.
That's the assumption. So he gets out his angle grinder. He grinds out the old, soft lime mortar. He packs in the hard, gray Portland cement. It looks crisp. It looks neat. He gets paid, and he drives away.
And then, 5 years later, disaster.
The wall starts to eat itself.
Okay, what is actually happening here? Because the sources describe 2 main ways this goes wrong and destroys the building. Let's start with the water.
Okay, failure mechanism number 1, moisture trapping. Remember what we said about the old wall? The old brick and the old lime mortar were a breathing system.
Right, the wick.
The wick.
Yeah.
Water got in, and the mortar acted like a wick to pull that moisture to the surface and evaporate it away. The mortar was the designated exit door for the water.
Oh, okay.
Now, you've repointed the joints with Portland cement. Portland cement is dense and waterproof. You have effectively sealed all the exits. You've corked the bottle.
So rain still soaks into the porous old brick?
But it can't get out through the joints anymore. It's trapped inside the wall. The moisture level builds and builds.
And it has to go somewhere.
It has to go somewhere. So the water is forced to travel through the phase of the brick itself to evaporate.
And that's bad.
It's catastrophic. As that water evaporates from the brick phase, it leaves behind any dissolved salts from the ground, from pollution, or even leached from the new cement itself. These salts crystallize just behind the surface, inside the pores of the brick.
And crystals expand when they grow.
With incredible force. It's a process called subfluorescence. It's like microscopic dynamite going off inside the clay. It literally blasts the face of the brick off. We call it spalling.
So you look at the wall, and the mortar joints are sticking out, looking perfect and strong, but the bricks all around them are scooped out and crumbling into dust.
Exactly. The repair is intact, but the historic fabric of the building is being destroyed from the inside out.
That is just heartbreaking. Okay, and what is the second failure mechanism, the thermal one?
Failure mechanism number 2, thermal stress. Buildings move. It's a fact of life.
Right.
The sun hits a wall, it heats up and expands. Night comes, it cools and shrinks. It's a constant slow dance.
And the old lime mortar, being soft, it could handle that movement.
It was flexible. It was like cartilage between your bones. It cushioned the movement. If the wall shifted and the lime mortar developed tiny cracks, it had this amazing ability to self-heal over time as new lime leached into the gaps.
But Portland cement doesn't self-heal.
No. Portland cement is rigid and brittle. It's like replacing your cartilage with steel rods. When the soft historic bricks try to expand in the summer heat, the rigid mortar doesn't give an inch.
So something has to break.
And since the modern mortar is much, much harder than the ancient brick, the brick breaks.
It loses every time.
Every single time. We call it the pinching effect. The hard mortar jaws clamp down and crush the edges of the bricks. You'll see these hairline cracks running vertically through the bricks themselves, originating at the mortar joint.
It's like the nutcracker effect. The mortar is the nutcracker and the brick is the nut.
That's a perfect analogy.
Mm-hmm.
By trying to make the wall stronger, we made it brittle. We destroyed its ability to accommodate life and movement.
This must have led to a massive realization in the preservation community. I mean, the lost art wasn't just about nostalgia for old-timey methods. It was about survival.
It was a huge wake-up call. In the late 20th century, conservationists and architects started seeing these failures everywhere and connecting the dots. They realized we were destroying our heritage with our best intentions.
So we had to relearn the old ways.
We had to go back to the textbooks. We had to go back to the kilns. There has been a resurgence in manufacturing traditional lime putty. We're training a new generation of masons to understand that patience is a virtue. And more importantly, to understand the most critical rule of restoration masonry.
Which is?
The mortar should be weaker than the brick.
That's so counterintuitive.
It is, but it's essential. The mortar is supposed to be sacrificial.
Explain that.
Over 100 years, something in that wall is going to erode from wind and rain. You want it to be the cheap, easily replaceable paste in the joints, not the priceless 300-year-old handmade brick.
The mortar takes the bullet for the brick.
Exactly. It's designed to fail slowly, so the more important parts of the building can survive.
It really challenges our modern mindset. We always want the high-performance spec. We want the strongest, the hardest, the most durable. But in this ecosystem, soft and porous are the high-performance specs.
It is a lesson in systems thinking. You cannot just swap out one component of a system for a better one without considering how it interacts with everything else. A historic wall is an ecosystem. Portland cement is an invasive species in that ecosystem.
So where does that leave us today? If I go to the hardware store for a project, I assume I'm still buying Portland cement.
For your driveway or a new concrete patio. Absolutely. Portland cement is fantastic for modern concrete. It allows us to build the world we live in. It is not a bad material.
It's just a specific tool.
You don't use a hammer to fix a watch. It's the wrong tool for the job.
Yeah.
If you're building a modern home with modern hard bricks and steel lintels and control joints, Portland-based mortar is fine. It's part of a rigid system. But if you are touching anything built before, say, 1930, you need to stop and ask, how is this building designed to work? How does this building breathe?
It's really coming full circle. We started with the burned thoroughly waterproof bricks of Babel, moved to the breathing walls of the Middle Ages, rushed into the chemical rigidity of the Industrial Revolution, and now we're looking back. We're trying to remember.
We're realizing that the old masters, the builders of the cathedrals and the colonial cities, they knew something we forgot. They understood compatibility. They understood time.
I love that arc. It's not just a straight line of progress. It's a loop. We had to learn what we lost.
It is. And it makes you wonder about the future, doesn't it?
How so?
Well, if we connect this to the bigger picture, we're doing the same thing today in different ways. We solve problems with new chemistry. We invent spray foams, plastic house wraps, complex sealants. We're sealing our modern buildings tighter and tighter to save energy.
We're living in Ziploc bags now.
Basically. And we measure success by R value, or air tightness right now. Those are the metrics. But we rarely ask, what will this new, unproven system do in 100 years? What are the unintended consequences?
We're building for the quarterly report, not the millennium.
The Romans built for the millennium. We build for a 30-year warranty, if we're lucky.
So here is the provocative thought to leave our listeners with. We just spent all this time talking about how Portland cement, the miracle material of the 1800s, turned out to be a destroyer of historic fabric because it trapped moisture. Look around your own house today, or the next time you see a new building going up.
What is today's Portland cement?
Exactly. What miracle material are we stuffing into our walls right now? Some kind of spray foam, a new peel and stick membrane maybe, that will make future architects shake their heads and say, what were they thinking? They trapped all the moisture and rotted the structure from the inside out.
Are we creating the restoration crisis of the 22nd century right now in our own homes? I would say. Almost certainly.
Well, on that terrifying note, thank you for taking us on this journey. It has been a blast.
My pleasure. Keep looking at the walls. They have stories to tell.
And to you, the listener, thanks for joining us on the deep dive. Next time you walk past an old brick building, take a close look at the mortar. Read the story in the wall. It's been through a lot. We'll see you next time.